Hello everyone, welcome to my talk. The title is Dynamic Pricing Provides Robust Equilibria in Stochastic Ride-Sharing Networks. And this is joint work with my advisors, Peter and Eva. So we're interested in mechanism design for ride-sharing networks. Specifically, we're asking the question, can prices incentivize drivers to take trips which maximize the social welfare generated by the marketplace? And this is an important problem because in modern ride-sharing networks like Uber and Lyft, drivers are autonomous agents who take trips of their own volition. So designing pricing policies which induce good strategic behavior is fundamental to achieving good performance of these markets in practice. And our results are going to be the following. So we're going to introduce a new model of stochastic ride-sharing networks which combines many of the previous elements studied only in isolation. And we're going to design a novel method to obtain tractability yet realism. And this is going to be called the stochastic fluid model. And we'll show how the stochastic fluid model can be used to obtain incentive-compatible prices. And next, we're going to demonstrate that dynamic pricing is fundamental to achieving good strategic performance in practice. And we'll do this by proposing a dynamic mechanism which satisfies a new robustness property that states every equilibrium we induce is going to be welfare optimal, not just the equilibrium we hope the drivers will play. So I'll start with a simple example illustrating our model dynamics and how prices enter the system. So it's going to be a very simple example with 2 time periods and 1 location. In the first time period, there are going to be 10 drivers located at the 1 location, and they're just going to make a decision about whether to exit the market and collect utility 1 for outside work, or stay in the market and collect utility based on the dynamics of the second period. So the dynamics in the second period are going to proceed in a sequence of steps. And the first step is that a stochastic scenario is going to be sampled from some exogenous distribution. And this stochastic scenario you can think of as modeling high-level uncertainty in traffic patterns or phenomena that affect the amount of demand in the city. So in this example, we're depicting weather scenarios. So we have a sun scenario and a rain scenario. But you could also imagine rush hour traffic patterns or what time a sports game might end. Next, the platform is going to observe the market state. So that's going to include the realized scenario, as well as how many drivers remained in the system, as well as how many riders are interested in a trip. And it's going to set a price. Next, prices are going to filter demand. So riders are going to have private willingness to pay values, and they'll request a trip if their value exceeds the price, and leave if not. And then drivers are going to be allocated trips based on how many riders requested a price, and they'll collect utility, positive utility for the price of the trip and negative utility for driving. And our most general model is going to be called the stochastic 2-level model. And in this model, we're going to assume that riders and drivers are discrete agents, and there's going to be a second level of randomness. In contrast to the top-level stochastic scenarios, there's going to be a second bottom level of randomness that corresponds to granular rider and driver decisions about whether or not to exit the market, and also what are their individual willingness to pay values. So in general, our model allows for multiple locations, multiple time periods, and we include a stochastic scenario tree modeling uncertainty in levels of supply and demand across time in our marketplace. And in particular, this stochastic scenario tree is a new ingredient we introduce for modeling stochastic ride-sharing networks. And as I mentioned, the stochastic 2-level model is our general setting for studying stochastic ride-sharing networks. Riders and drivers are going to be discrete atomic agents. We have macroscopic randomness modeled by the stochastic scenario tree, and microscopic randomness modeling individual rider and driver decisions about whether or not to enter the marketplace and what are rider willingness to pay values. And so we're interested in this setting sort of at a large market limit where the number of riders and drivers grow, but the other population parameters remain fixed. And in order to obtain a tractable approximation to the complicated dynamics with all these individual decisions, we're going to introduce what we call a stochastic fluid model. And the stochastic fluid model you can think of as our tractable approximation to the stochastic ride-sharing model. And in this model, we're going to assume that riders and drivers are continuous agents, and we're going to assume that the microscopic level of randomness governing rider and driver decisions is going to become deterministic. Importantly, emphasize that the stochastic fluid model retains the macroscopic randomness modeled by the stochastic scenario tree. And this is in contrast to standard fluid approximations where all demand, or all randomness will become deterministic. Here we're retaining the top level uncertainty from the scenario tree. And so I've mentioned that this is a tractable model for the dynamics of the two-level model. What I mean by that is in the context of the stochastic fluid model, we show that the welfare optimal plan, that is the welfare optimal sequence of trips across space and time and every possible scenario realization, can be formulated as the solution to a convex optimization problem. And solving this convex optimization problem is going to be the key tool that we use for getting prices that are incentive compatible. And so as motivation for our final mechanism that we propose, I'll start by describing a similar mechanism that uses similar techniques. So this mechanism is going to be called the static pricing mechanism, and it's going to operate by solving the stochastic fluid problem just once at the beginning of time before the marketplace dynamics play out. And what we're going to do is obtain prices from the dual variables of the solution that we compute, and the dual variables are going to give us prices for every origin, destination, time, and possible realization from the scenario tree. And the motivation for studying the static mechanism is it comes very close to solving the problem that we initially set out to solve. Namely, what we show is that the welfare optimal trips, i.e. the primal solution that we computed at the start of the time horizon, is an equilibrium for the drivers under this static pricing mechanism. So that seems on the surface to be really good news. However, some very bad problems can occur when you use static prices in this manner. So those problems are going to be that the equilibria we induce are not unique, and some of the equilibria that can be induced under the static mechanism are going to have arbitrarily bad equilibria from the perspective of social welfare. And next, our original motivation was to develop prices that are incentive compatible for the two-level model. And when we take the static pricing mechanism and use it back in the context of the two-level model, small discrepancies between stochastic demand and expected demand can cause us to lose incentive compatibility entirely. So what do I mean by this? Well, let's return to the example with 2 time periods and 1 location and explore what static prices do in a little bit more depth. So the static pricing policy is going to operate first by formulating an optimization problem based on this network, and it's going to produce a pricing policy that sets prices based only on what the realized scenario is in the second time period. So in particular, the pricing policy is not going to adapt its pricing decisions to the number of drivers that remain in the network at the second time period, because that information isn't available at the time when the static pricing policy solves for the optimal plan. And the first problem that can occur is that by not resolving, we're going to be in a situation where the equilibrium strategy is not unique, and this problem is actually going to be fairly ubiquitous because of the structure of the optimization problem that we solve. So based on the convex optimality conditions, the static pricing policy is going to produce the following property. So the utility between, so in the static or the stochastic fluid model, under the static pricing policy and under the socially optimal strategy for the drivers, the utility between the exit action and the stay action is going to be completely equal from the perspective of the drivers. However, since we're not recomputing prices based on the observed number of drivers in the second time period, the prices are not going to change if there are too few drivers who remain in the system in the second time period. This means that an alternative equilibrium is for all drivers to just exit in the first time period and collect utility 1. However, clearly this is a bad equilibrium for social welfare because we're missing out on many potentially high-value trips in the second time period. The second problem that can occur, and of potentially even greater consequence, is that when we take the static pricing policy and use it in the context of the stochastic two-level model, the small discrepancies between stochastic demand and expected demand can cause us to lose incentive compatibility entirely. And the problem is that because the stochastic fluid model, or in the stochastic two-level model, no matter how small the variance, there will always be some small probability that fewer riders than expected came to the platform and requested a dispatch. And in these cases, some small fraction of drivers are not going to get a dispatch when they otherwise should have in the context of the stochastic fluid model. So by taking these prices and using them in the context of the stochastic two-level model, the expected utility for drivers who stay is going to decrease ever so slightly because of these discrepancies between stochastic demand and expected demand. However, the expected utility of exiting in the first time period will always be 1. It's just a constant. So in this case, it would actually strictly be better for the drivers just to exit. So our solution to this problem, as you might have guessed, is to use dynamic pricing. So when there are too few drivers who remain in the second time period, we're going to somehow recompute prices so that drivers are incentivized to not all exit. And the ultimate mechanism we propose is called the stochastic spatio-temporal pricing mechanism, and it does just this. So the stochastic spatio-temporal pricing mechanism is going to resolve the stochastic fluid problem at the beginning of each time period using the observed current spatial driver distribution in the marketplace.
Quick question.
Yeah.
What about the realized scenarios? Do you plug them into the...
Yeah, oh, yeah, it also recomputes the optimum based on the realized scenario, yeah.
And kind of a follow-up question, so at time 0, so when you calculate the static prices,
yeah.
How should I think of them? Because the scenario hasn't been, no scenario has been realized yet, so...
That's right, yeah. So when we compute, when we solve the optimization problem for the static mechanism, the entire scenario tree is embedded into the optimization problem that we solve. So this gives us a price to use for any possible realization of the scenario. So the prices are static. They can still adapt to the scenario, but what I mean by static is they're not adapting to the small discrepancies in supply or demand.
So you should basically get the vector of all the future scenarios as a parameter, and then the static prices are going to be functions of those parameters?
Yeah, exactly. So in the stochastic two-level model, our results are going to hold in a large market limit where the number of riders and drivers scales to infinity at the same rate. And I'll also mention that we assume drivers are expected utility maximizers. So our first result is an incentive compatibility result stating that following the optimal primal solution computed by the stochastic spatio-temporal pricing mechanism in each time period, is an approximate subgame perfect equilibrium for the drivers under the prices set by the SSP mechanism. And this result you can think of as an analog to previous results in mechanism design for ride-sharing networks. In particular, there's this paper by Ma, Feng, and Parks, which obtains incentive-compatible, subgame perfect, welfare optimal prices in a deterministic model of ride-sharing. And so here we're extending this style of results to a setting with stochasticity. And next, we demonstrate the criticality of dynamic pricing for achieving good strategic outcomes by showing that our dynamic SSP mechanism satisfies this new robustness property. Namely, every approximate equilibrium induced by our pricing algorithm is approximately welfare optimal. So this style result is really beneficial for the operation of these marketplaces in practice, because we don't have to assume that drivers are going to play one equilibrium over another. As long as they play any equilibrium, this result tells us that we are guaranteed to achieve close to optimal social welfare. So the takeaways are that I've introduced a new stochastic ride-sharing model with spatial and temporal components and shown that a stochastic fluid approximation retains top-level uncertainty and yields a tractable approach for computing incentive-compatible prices. And finally, resolving is critical for achieving good strategic behavior in these marketplaces. Thank you.
Two quick questions. One is, you said that the expected utility of exiting and staying happens to be the same under it's just solving the first problem.
Yeah.
Is that because it kind of lacks strict convexity in the individual utilities? Right, because usually that means there's several feasible points which do not match the matching demand and supply, even though it satisfies strong convexity. But that might be too technical of a question.
Oh yeah, okay. It's interesting.
Math,
I think not. I think not, but we could discuss it more.
And then I guess the second question is, have you just considered like a simple dual update, right? Essentially what you're doing is you're solving the primal problem and then you're just using the dual variables. But I suspect that the problem simply decomposes into something like what the drivers want plus what the users want solved individually hooked together by prices, right? This is like some thin-shell conjugacy style result. And then have you just considered, instead of kind of resolving the problem using the prices, just doing like a gradient update?
No, that's a good, yeah, I guess if you were to do this in practice, you could definitely consider doing something like that.
Right. It would also smooth out things like stochastic changes as well. So it might be interesting. But we can chat about it more later too.
Great.
Question from the online. Richard Cole says, if there are multiple equilibria, why would drivers play the same equilibria?
It's a great question. Yeah, that's kind of true for a lot of these questions. Yeah. I will say that the kind of structure of the multiple equilibria is a little bit misleading. We do have strong convexity in, or like strict convexity in the utility, the reward functions that are associated with trips that we serve. The linear component of our objective function has to do with like costs of driving and exiting. So like when I say there are multiple equilibria, they tend to be of the structure that I could leave now and collect utility 5, or stay and then leave in the next time period and collect utility 5, and they don't matter so much. I guess I'm saying it's not quite a theorem, but all the equilibria, actually it is a theorem. We do show that all the equilibria serve all available dispatch demand. So I don't know. That's a bit of winding, but in general, how do people agree to plan on equilibria? Yeah.
So just maybe a clarification about this. First of all, nice talk. About the static pricing, is it arbitrarily bad in terms of welfare, or so what do you mean?
Yeah, it can be because the welfare depends on rider values as well. In the example I showed, if you have, you can construct like sequences of examples where the maximum rider value goes to like infinity, but the utility generated by the drivers staying 10. So yeah, because they're not serving any rider welfare and any riders, and rider welfare can be arbitrarily large, it is arbitrarily bad.